Special theory of relativity or relativistic mechanics. This is the main topic on which I have to discuss. Einstein was the person who basically developed this theory in 1905 and shared this knowledge with his science community. Actually, Newton was the person who laid the foundation of classical mechanics. What is the classical mechanics or Newton mechanics? You can say that if there is a particle or a body of mass m, you apply some force on it. As a result, this body starts to move. That means it's have a velocity, acceleration, and it displays up to the some distance that you can say d. As a result, you have observed the kinetic energy, total energy that you define in terms of the momentum p. And here Newtonian equation, second law, that F is equal to ma, is very important to define all these parameters. So kinetic energy, total energy, momentum, velocity, acceleration, displacement, all these parameters are basically kinetic energy. If you write here, that is equal to p square upon 2m, or in terms of mass and velocity you can write it in this way. So p square upon 2m is also kinetic energy. If you will put the value p, that is equal to mv, and here put that value here, you will get this 1 by 2 mv square. So all these basically parameters are important to define the mechanics, and that mechanics first of all defined by the Newtons in a proper way. And what basically Einstein did here, Einstein observed all physical observables by using the concept of reference frame. So Einstein had this thing that instead of he introduced the concept of reference frame. So if I make this coordinate system here, then obvious the mechanics of this particle you will see here have velocity and force, kinetic energy, etc. But right now that all the physical observables are with respect to this coordinate system, the origin. So this is the additional part which Einstein basically introduced into the mechanics, and because of that we say relativistic mechanics. Right, so physical observables means here the displacement, mass, velocity, acceleration, force, momentum, kinetic energy, potential energy, total energy, etc. What you right, and so all these observables which we can observe. So here the first concept comes of the reference frame. What is that? That you can define it in a simple way. A coordinate system is basically a reference frame. Here you can see the coordinate system with the x-axis, y-axis and z-axis. This is the origin O, and if there is a point P in this coordinate system, you can define that in spatial coordinate x, y, z and the time coordinate. So these four coordinates are important to define this P point. Actually, point is the event, and event you can define in terms of the x, y, z and t. So this is very important concept here. So and now further, event is what? Event may be the explosion of a bomb. Event may be like I am talking with you at my platform. This is also event. Event may be a function of birthday, function of marriage. Whatever you see basically, that is a event, right? So that event you define in terms of x, y, z. That means the position, that means the place. T means the time. Everything whatever you observe in your life, that you define in terms of the position, that means place, and the time. You will say that you were born at that place at that time on this day, right? So all these information basically comes through this coordinates system. So event is that, right? And now the second point, if this is clear to you, the types of the reference frames. Reference frames are of two type. One is inertial, second is non-inertial. So to understand it clearly, I have made this picture. This person is standing on the surface of the earth. That man represented by the O, and a coordinate system is associated with it, right? That you can say the surface is a coordinate system. We have represented that with a coordinate system, and there is a man O prime, I am saying to that, is on boat, and boat is in river, moving towards this direction with the velocity v. So a coordinate system is associated with it, that is the boat, right? So here I have made a reference frame S prime, this boat, and this is the observer. So this man is standing on the boat, and boat is moving into the river into this particular direction, and here a man just is standing, and you can say watching to the second man O prime. So now you have to tell that is this observer is in inertial frame, or is this observer O prime is also in inertial or non-inertial frame. Simply define that inertial frame are those frames where those either in rest position or have a constant velocity. Uniform motion you can say, right? Only then that reference frame will be inertial, and in case of non-inertial, that will be a non-uniform motion. Non-uniform motion means non-uniform velocity. That means there will be acceleration. Here you will find the acceleration, and in the above case acceleration is 0. So this is a simple identity to find the inertial and non-inertial frame. Here you have to tell, does this frame S prime is inertial or non-inertial, while this velocity of the boat is constant. So what is your answer? This is inertial or non-inertial? And this man is in rest position, and here this tree, the other small plants that represent basically through this coordinate system S. So this man is in inertial frame or non-inertial frame. My question is this. And similarly for this frame S prime frame is a boat that is moving in a river with the constant velocity v, and a man is standing into the boat. Does this S prime frame is inertial frame or non-inertial frame? What is your answer for the S prime? Yes, this is inertial frame. Why inertial frame? Because this frame is moving with constant velocity, and here this is the definition, simple definition in simple words of the inertial frame. And here no doubt this frame is in rest, so it will be inertial frame. So both the frames associated with the observer O and O prime are inertial. Now into the next section. So inertial reference frame are simply when acceleration is 0, then you can say that frame is inertial frame. If the reference frame is either at rest or moving with uniform velocity, that frame is inertial frame. Non-inertial reference frame simply moving with non-uniform velocity. So what are the possible examples which you think that these are inertial frame or non-inertial reference frames? Actually, first point is that reference frame may be anything. It can be anything. like a car, a train, earth, other planets, bus, aeroplane, spacecraft, rocket, whatever you can think, that may be a reference frame. A house means anything with reference to that you can define the event, that may be a reference frame. So here, first of all, the observation of two different people, uh, right, how they see any event, we have developed a relationship between the coordinates, and that comes out through the Galilean transformation. To make it more clear, suppose I have a frame of reference S, that is x, y, z, and observer is at O position, that you can see is this man standing here, right? This is observer O. And a second frame of reference, this one, that is denoted by x prime, y prime, z prime. Here is observer O prime, and there is an observer here, you can see, right, is in moving frame, and that is denoted by S prime. This S prime frame actually is a, you can say here, like a car. And man actually sitting here, driving the car, right? So this person is sitting into the car, and this car is a frame of reference, that is denoted by S frame. Here man is standing across the road. Here this man is standing across the road. This is the situation, right? So this situation, this particular situation, the last one which I have made, the man is standing across the road, and right here you can see under the tree, and this car is moving. So this man basically, who is standing across the road here, is represented by the observer O, that is in rest. The car is moving with some speed, you can say 60 km/h, and this is constant with respect to this man, so that is denoted by the V. So this V is the relative velocity with respect to this person, and this moving frame, as I told you, S prime. So what basically a phenomena happens into the S prime frame, a bomb basically explode here, right? So the coordinates according to the O prime observer, they will be x prime, y prime, z prime. He will say that this bomb explode at this particular position and at this time, and the man who is standing across the road, he will say that it happens at x, y, z and t time. So right, so this is the situation, this is the physical situation. This man observe in his frame of reference, this man observe in his frame of reference according to his coordinates, right? So you mathematically you can see, so here that this distance from this observer is x prime, this distance with respect to this origin for this O prime observer, and for this observer this distance will be x. And at any time t, the distance between the O prime and O will be velocity into time, where v is the velocity, this relative velocity. If you multiply velocity by time, you will get the distance. So at any time t, this is the distance between O and O prime, right? At t is equal to 0, what will happen? This will be equal to 0, and this S prime frame will coincide on the S frame. So then that time O and O prime will coincide at t is equal to 0. O is equal to O prime. That means both the frames will coincide. And I want to tell one more important thing here, that this speed is very small as compared to the speed of light, but for the purpose of explanation or to make it simple, I have used 60 km per hour. Otherwise v is near about to the speed of light, that is the c, 3 into 10 raised power 8 meter per second. So what basically is the observation of the O prime for this event, and what is the observation of this observer O for this event, right? We have to find out that solution, what basically they are observing. And to make it more simple further, that what is my purpose here, right? If you are sitting in a train, this is the train, right? No need to make again. So this is a train, you are sitting, you were when you were child, then that time you observe that plants, tree moves in opposite direction to the direction of train, right? If your train is moving in this direction, you observe that plants or tree were moving into the opposite direction with the same speed as of the your train. So v is in positive direction, plants are moving in opposite direction, the velocity is same, that is minus v, right? So this is the point. And so here one observer who is sitting into the train observe that plants are moving in opposite direction, right? And the person, the observer who is standing across the road, observe that plants are stationary, they are not moving, right? So his observation is also true. And the person, the children or the child who is sitting into the train, he observed that plants are moving in opposite direction, that's observation is also true. So now the point is that, is this person who is standing on the earth is wrong? No, because now we are aware that plants or tree does not move, right? So we can say that time the observation observed by the child was true, and this is also true. And it depends on the speed of the relative motion, which we will discuss further. But the point is here, we have to develop a relationship that what the observer who is stationary, who is at rest, observe that event into the moving frame, right? Our main purpose is that what is the observation of O in S prime frame and observation of O prime in S prime frame, right? This is the real, the observation is true for this O prime, but how this observer O looks at the event into the S prime frame. So we have to develop a relationship, and that relationship we found with the help of some transformation equations or relationship between the coordinate systems, right? We have to discuss that here. And first of all, that is the Galilean transformation. Here Galilean transformation are used for transformation of position, coordinates and time from one inertial reference frame to the second one. The two references frame are shown below. You can see this S and S prime. S prime is moving with relative velocity v with respect to the S frame. P is an event which occur into the S prime frame, and the coordinates of that event according to this observer O are x, y, z and t. According to the O prime observer, they will be x prime, y prime, z prime and t prime. The distance of this event from the observer O will be in the unprime frame, and the distance of this event will be in prime frame according to the O prime observer, that is x prime. So here you look that this is x, this is x prime. Now what is the distance between O and O prime? At any time t, you know this is the velocity, relative velocity, that is constant. So at any time t, the distance between O and O prime will be vt. So these are some points, assumptions. Now at any time t, you know that this x from p to O is equal to vt plus x prime written here, and the perpendicular component along the y-axis and z-axis, they remain same, right? Because the event height is same for both the observers and along the z-axis also. So y is equal to y prime, z is equal to z prime, t is equal to t prime. So this is the main point in the Galilean transformation. So now we have relationship x prime is equal to x minus vt, y prime is equal to y, z prime is equal to z, and t prime is equal to t. Actually t prime is equal to t. In Galilean transformation there is no change into the time. They assume that time is absolute. Time is absolute. There is no change into the time, right, up to the Galileo. So there is no change into the time because of the relative motion. No change in time because of the relative motion. So by this way one can define these coordinates x prime, y prime, z prime in terms of the unprime frame x, t, y, z and t, this, right? So the purpose to develop these equations is that O observer knows their coordinates, that they are x, y, z and t, right? O observers knows is the observation, the position, the time, the place, everything he knows. So if he want to visualize the event which occurs into the S prime frame, then he can find out the coordinates of that system by using these relationship in his system. This is very important point, right? So with the help of O observer x, y, z and t, he can visualize the event into the S prime frame. With the help of x, y, z and t, observer O can assume or define the event in moving frame, that is S prime, right? So this x prime, y prime, z prime, t prime, so that event x prime, y prime, z prime and t prime. So this is the Galilean transformation, and now we will see that, and now we have this set of equation x prime is equal to x minus vt, y prime is equal to y, z prime is equal to z, t prime is equal to t. So now if we suppose that we apply some force, this is a particle of mass m, and we apply some force on that, it starts to move with velocity v, then that time it will have momentum, kinetic energy, everything which basically required into the mechanics, right? So we have to find out now the component of the velocity, component of the momentum, energy of this particle into the S prime frame. The velocity of particle mass m have ux along the x-axis, uy along the y-axis direction, and uz along the z direction. X, y and z direction, you can see, right? And I have to find out the acceleration, then I can find out the acceleration ax, ay or az along the xyz direction. So with the help of these equations, x prime, the first one, ux prime is equal to dx prime upon dt prime is equal to dx prime is equal to x minus vt. X minus vt is equal to dx upon dt minus v dt upon dt. As I know from this equation that t prime is equal to t, so I can write here dt prime is equal to dt. So instead of this dt prime I can write here dt. So this is dx upon dt minus v, that this v is the relative velocity. Don't confuse with this v with this ux prime. This velocity is the velocity of the particle in a moving frame. So this dx upon dt is, you can say, ux minus v dt cancel out, so here you are getting ux prime. And for this equation, uy prime is equal to uy only, uz prime is equal to uz. And further, with the help of this equation, you can find out the acceleration of that particle. Ax prime is equal to dux prime upon dt prime, that means d upon dt. I can write dt prime is equal to dt and ux minus v. This dux upon dt minus dv upon dt. Dux upon dt is equal to acceleration of the particle in unprime frame, and v is constant, so dv upon dt is equal to 0. So here you observe that ax prime is equal to ax. Similarly, you can find out ay prime, that is equal to ay, az prime is equal to az. I can write ax prime here is equal to ax. If you see carefully these equation, it says that the acceleration is constant in prime frame and unprime frame for both the observers of that particle. What it concludes, basically, if we have conclude the result, what we can conclude from this one, we are saying that particle which is moving into the s prime frame having the same acceleration as into the s prime unprime frame. Here ay prime is equal to ay, az prime is equal to az. If acceleration is constant, it means both the frames are reference frames are inertial. This is the conclusion of the Galilean transformation. Thanks for watching this video. If it is helpful to you, please like, share and subscribe the channel. For such video you can see my blog www.apniphysics.com. For more update you can see Facebook page with /apniphysics. Myself Sushil Kumar. Right, if you have any question or doubt, you can message me.